Welcome to my lesson on vector spaces and algebras. This is the last lesson in my series on abstract algebra. I also have another playlist on linear algebra that goes well beyond vector spaces, and if you're interested in that topic. And I'll put a link to that playlist in the information to this video. A vector space over a field F, in most cases it's either the real numbers or the complex numbers, is a non-empty set V together with two binary operations, which I'll define below. The elements of V are called vectors, and the elements of F are called scalars. Vectors are usually represented either in bold or with an arrow, and sometimes just by context. I won't use either, but normally I try to use both, at least in this lesson. One of the binary operations is vector addition. This operation assigns to any two vectors, u and v, the third vector in v, which is written u plus v, and called the sum of these two vectors. The other operation is scalar multiplication. This operation assigns to any scalar in our field and any vector v, another vector a times v. In addition to the two closure axioms, these two here, a vector space must satisfy the following axioms. The set V must be an abelian group under the vector addition operation. The group identity is represented by the symbol 0, and we've seen that before in my other lessons on groups and rings and fields. Caution here, the field F also has an additive identity, which is represented by 0, not bold. So we have two different zeros, which can cause confusion in some of the proofs. So I'll try to point that out where there may be confusion. Compatibility of scalar multiplication with field multiplication. So A times BV equals AB times V. Identity element of scalar multiplication. So there exists an identity in our field such that 1 times any vector from the vector space equals the vector itself, where 1 is the multiplicative identity of the field. Distributivity of scalar multiplication. So you have the scalar times the sum, and you just have the scalar times each one added together. You have here, and then you also have distributivity of the scalar multiplication with respect to field addition. So here you have A plus B times V, and that's AV plus BV. Okay, so these two properties here, closure, and then these properties here together make the definition of a vector space. And I'll show you some examples which will maybe help clarify things. I have a few basic results on this slide, and you see right away where we have some of the issue with the two different zeros. For example, the first item here, you have the scalar 0 times v equals the vector 0. Then on the second one, you have the scalar times the 0 vector equals the 0 vector. Third one doesn't have the 0 possible confusion, but it's just saying the inverse of the multiplicative identity times any vector is the inverse of the vector. And then if a scalar times v equals the 0 vector, either the scalar is 0 or the vector is 0. So let's go about proving each one of these using the distributive rules for vector spaces, and this is the first one we're working on. We have 0, scalar 0 times v, and of course 0 plus 0 is a scalar, equals 0. So from here to here, we're okay. And then we use the distributive law to get this. Then adding the additive inverse of 0v to both sides, we get 0 on the left And then on the right we get the scalar 0 times v, and that's what we wanted to prove. All right, let's go to the second one, and we'll again use the distributive law. So we have any scalar a times the vector 0, and the vector 0 plus itself equals 0. That's because the vector space is an abelian group. Actually, it's just we don't need the abelian part, it's just a group, so the 0 added to any element is 0. And then you use the distributive law, you get this. Then using the same idea we did here, we add the inverse of a times the vector 0 on both sides of this. On this side, you cancel out one of the a zeros and you get a 0, and on this side, you just get something minus itself and you get 0. So that proves the second one. Then let's look at the third one here. So we'll take v plus a vector, any vector v, plus minus 1 times v, and the vector from one of the axioms of a vector space, this vector v is just 1 times v. Then we can use the distributive law to write this out. But then 1 and its inverse is 0, the scalar 0, and you get 0 times v. And then we proved in part 1 that 0 times v is 0. So in other words, we have v plus minus 1 times v equals 0, which means that this thing here is the inverse of v. Okay, so we have one last piece to prove here. If a equals 0 in this statement, then we're done, right? Because it says either a equals 0 or v equals 0. So we take this case first. If that's true, then we have nothing to prove. So let's say that a does not equal 0. Then a, being a non-zero element of a field, has an inverse. So in other words, a, and this is multiplicative inverse, exists. Then we multiply both sides of our given equation here, av equals 0, by a inverse. And we use part 2 of our theorem, which you've already proven. So we have a inverse times av, that's 1. Then 1 times v is just v. And then a inverse times 0, just looking on the other side of this, is 0. So just following the all the way through here, you end up with av. You end up with v equals 0, which is what we wanted to show. That was the other possible case. Let's look at a few examples on this slide. First one is the set of real numbers over the real numbers is a vector space under the usual addition and multiplication of real numbers. In this case, the vector space and the field equal the real numbers, as I stated here. The set of ordered pairs of real numbers is a vector space, and this is something you may have seen in physics and maybe like in high school or college. So here you have 2 ordered pairs, and the addition is just you component-wise, and scalar multiplication is the same way. You just multiply a scalar times each element in the ordered pair. And you have similar in 3 dimensions. I mentioned here n dimensions. The set of ordered n tuples of real numbers is a vector space over the field of real numbers. Addition and scalar multiplication are defined in a similar manner to the previous case here. So if you just had more elements in your tuple, you would just add them component-wise, and the same thing for scalar multiplication. The set of all polynomials with real coefficients is a vector space over the field of real numbers. Vector addition is accomplished by adding coefficients of like terms, i.e. terms of the same power, and scalar multiplication entails the multiplication of a given scalar times each coefficient in the given polynomial. So it's very similar to this previous example here. The set of all matrices with real coefficients over the real numbers is a vector space. Standard matrix addition is used here, and multiplication of a matrix by a scalar results in every element of the given matrix being multiplied by the given scalar. The set of all continuous functions from the real numbers to the real numbers is a vector space under the usual addition of functions and pointwise multiplication of functions by real numbers. The associated field is R, the real numbers. The set of all solutions to a system of linear equations with real coefficients is a vector space over the field of real numbers. And there's many more, but I just given you 7 examples here. I have a few concepts on this slide related to vector spaces. It's related to linear combinations of vectors and linear independence. First concept is a linear combination of vectors results in a new vector that is created by adding together scalar multiples of a set of vectors. For example, take u and v in our vector space V and scalars a and b from our field. Then the vector au plus bv is a linear combination of vectors u and v. And of course we could have done this for 3 or 4 or any number of vectors. I just took a simple case here. And of course this is still in V because of the axioms, the two closure axioms. A set of vectors is linearly independent, and sometimes we just say independent, if no vector in the set can be written as a linear combination of the other vectors. Then we have a couple of equivalent definitions of linear independence. A set of vectors is linearly independent if a linear combination results in the zero vector if and only if all its coefficients are 0. A set of vectors is linearly independent if two linear combinations of the set define the same element of V if and only if they have the same coefficients. So you can prove any one of these from the other. I won't do that here, but these are all equivalent. The definition I gave up here as well as these two. So for example, in three-dimensional Euclidean space, R3, the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 are linearly independent since there's no way of writing any one of the vectors as a combination of the other two. You notice they have a 1 in a different place and zeros everywhere else, so there's no way of writing any one of these in terms of the other two. A set of vectors that is not linearly independent is said to be linearly dependent. And I have an example here again from R3. So if we take these three vectors here, notice that this one here, 2 minus 1, 3, is 2 times this vector minus 3 times this one. We can check component by component. 2, then 0 here, so you get 2. Then 2 minus 3 gives you a minus 1. 2 times 0 minus 3, so that checks out. A linear subspace of a vector space is a subset of the vector space that is also a vector space. In other words, a linear subspace is a set of vectors that is closed under vector addition and scalar multiplication and satisfies the other properties of a vector space, many of which are inherited. We'll see that in the theorem that follows. For example, two-dimensional Euclidean space, R2 is a linear subspace of R3. Then we have a theorem. A subset U of a vector space V over field F is a subspace. And this is just shorthand for linear subspace. I'll normally just say subspace of V if and only if ax plus by is an element of U for all x and y, all vectors x and y in U, and all scalars a, b in F. So let's look at a proof. You have to go in both directions. Going in this forward direction is easy. If U is a subspace, and thus a vector space in its own right, then closure under vector addition and scalar multiplication implies that ax plus by is an element of U for all x and y an element of U, and scalars a, b an element of F. Going in the other direction, we need to check the different axioms. So we're given that ax plus by is an element of U for all vectors x, y, and U, and scalars a, b, and F. So we can write x plus y is 1 times x plus 1 times y, just getting it in this form here. And so that would give us closure for a vector addition. Then we can write 0 is 0x plus 0y. So that's, again, using this property. We have 0. The vector 0 is in U. Then for x in U, we have minus x is minus 1 times x plus 0 times y. I didn't even bother putting that in there, but just getting it in this form. So the inverse of x is in U. Then if you take these together, and note that the additive associativity and commutative laws are inherited by U from V, we have that U is an abelian subgroup of V. Ax is an element of U for every vector x in U and scalar a and F. That just, again, comes from this here. We can just write ax plus 0 times y. The other properties for a vector space, compatibility of scalar multiplication, and the two distributive rules are inherited by U from V. So thus U is a vector subspace of the vector space V. Okay, so the what this comes down to is we don't need to normally check all of these axioms. If we can just show that any linear combination of elements in some subset U of a vector space V is also in U, then we have that U is a subspace of V. In other words, it's a vector space in its own right. We have some more concepts on this slide. These are basically extensions of what we know from three-dimensional Euclidean space, which you've seen in high school, maybe some calculus classes, either in high school or college. So just keep that in mind as you see this here. A linear span of a set of vectors is the smallest linear subspace that contains the set of vectors. In other words, a linear span of a set of vectors is a set of all vectors that can be created as linear combinations of the vectors in the set. More formally, we can define a linear span as shown here. So the linear span, or just the span, of the vectors v1, v2 up to vn is the set of all linear combinations of those vectors over the given field. Then, very much related to a span is something called a basis. A basis of a vector space is a set of vectors that spans the vector space and is linearly independent. So it's kind of a minimal set from which you can write every other vector in your vector space as a linear combination. In other words, a basis for a vector space is a set of vectors that can be used to create any vector in the space, and no two vectors in the set, the basis I'm talking about, are linearly dependent. So for example, 1, 0, 0, 0, 1, 0, 0, 0, 1 form a basis for R3. That's what you would be familiar with the X, Y, and Z axis. You're basically writing everything in your three-dimensional space in terms of these three vectors. So when you're first introduced to three-dimensional space, it's not normally posed in these words, but that's kind of the idea. more generally, is stated here. In general, there are many bases for any vector space. So for example, these three here, I could take any one of these and multiply it by any real number. I can take this middle one and multiply it by 3 or 5 or 7 or an infinite number of different numbers, and each one would still be a basis with these other two. Or I can multiply all three by different numbers and I would get another basis. So there's an infinite number of ways of doing that. However, it can be shown that the number of vectors in a basis for a given vector space is the same for all bases. So in R3, even though there's an infinite number of different bases, it's always three of them that form a basis, not two or not four. It just has to be three in the case of R3. The dimension of a vector space is the number of vectors in a basis for the space. It is also possible to have infinite dimensional vector spaces. For example, the set of all polynomials with real coefficients, the set of all continuous functions on the real line, and the set of all sequences of real numbers are infinite dimensional vector spaces. As I noted on the previous slide, the concept of a basis, linear independence, and spanning set are related, and I have a theorem here on this slide that relates those some of those concepts. So let V be a vector space with vectors v1, v2 to vn. Then the following holds true. V sub j, excuse me, element is an element of the span for j equals 1, 2, up to n. The span of these vectors is a subspace of V, and if U, some subset U of V, is a subspace such that V1, V2, up to Vn is an element of U, then the span of the vectors V1 to Vu is a subset of U. So the first part is simple. It's almost obvious to say that Vj is in the span of these vectors. Since it's one of those vectors, you just write it as 0 for the coefficients here, and then just the 1 times Vj, V sub j. So that gives you this here. That's, as I say, pretty obvious. By the definition of linear span, the span of these vectors is closed under vector addition and scalar multiplication, and thus is a subspace of V. That was a theorem we had from the previous slide, 2 slides back, theorem 27. And since U is a subspace of V, we're given that, it is closed under vector addition and scalar multiplication. And since we're told that these n vectors are an element of U, that implies that the span is a subset of U. Okay, so that's this theorem. Let's continue. We have a few more theorems on this slide. If V equals the span of these vectors here, V1, V2, up to V sub n, then either S, the set of the vectors, is a basis for V, or some subset of S is a basis for V. So we have a proof. If V is an element of S, it can be written as a linear combination of the other vectors in S. Then we can just remove it, and S minus V also spans V. Then we do the same thing again. If U, an element of S minus V, can be written as a linear combination of the other vectors in S with V removed, then S minus U and V, in other words, U and V removed from S, spans V. And we can continue in this manner until the remaining vectors are linearly independent while still spanning V. In other words, until we've found a basis. Then very quickly we have this theorem 30, or very immediately we have this theorem 30. Every finite dimensional vector space V has a basis. Since V is finite dimensional, it has a finite spanning set, which we'll call S, having these vectors in it, such that V equals the span of these vectors, V1, V2 up to Vn. It then follows from theorem 29 that V has a basis. If V is a finite dimensional vector space, then any two bases for V have the same number of elements. And I'm not going to prove that here, but it's theorem 542 in an online book, Linear Algebra. I'll give you a link to that in the information to this video. If we take two vectors, x and y, and vectors from a vector space V over a field F, we can write them uniquely in terms of the basis, which I'm showing here, V1, V2 to Vn. That's actually a theorem to show that this is unique, but it's pretty easy to see that why it is the case. If we were able to write x in terms of the basis two different ways, in other words, where some of these coefficients were not the same, and then you subtracted those two representations, on the left you would get 0, and on the right you would get a linear combination of the basis vectors where at least one of the coefficients was not 0, which would contradict the basis vectors being independent. So that's sort of a quick verbal proof. In any event, we have this representation here. The scalars x sub I and y sub I in the above equations are called the coordinates of x and y over a given basis. Another terminology is to call them the coefficients of decomposition of x and y over the given basis. And another way of writing this is the shorthand shown here, where you just write them as tuples, and it's understood that these are from the given basis. And if we gave a name to this basis, say we called it capital B, then we might want to put a little subscript, capital B, under with the x, and as well with the tuple here, and the same for y, just to emphasize that it's with respect to the basis B. I didn't do it here, but you'll see that in some cases. A coordinate vector is a representation of a vector as an ordered list of numbers that describes a vector in terms of a particular ordered basis. And then we have also that the set of n tuples, for example these here, with elements from F is a vector space denoted F superscript n, with addition and scalar multiplication defined as you might suspect, just pair pointwise addition and then scalar multiplication. You just multiply the scalar times each term. Take vectors x and y defined in terms of their coordinates. Then the inner product of x and y is defined as the product of each component in the same position added together. So for example, if we had x and y is defined here over F3, so that would be, F3 would be the integers mod 3, it would just be 0, 1, and 2, and then 3 is 0, and 4 is 1, and so on. So if we take that dot product, we have 1 times 1, 2 times 1, then 0 times 1, 1 times 0, 1 times 0, we get this here, and that adds to 3, but that's 3 is 0 in F3. Then the dot product of x and y, if that equals 0, then x and y are said to be orthogonal vectors. When a vector space is defined over a finite field, it is possible for a vector to be orthogonal to itself. I have an example of that. If we let x equal 1, 1, 1, 1 over F2, then the dot product is 1 plus 1 plus 1 plus 1, and that's 4, which is 0 mod 2. It's also possible for a vector to be orthogonal to itself when defined over some infinite fields, not all. So for example, consider the vector space, two-dimensional complex vector space, complex numbers, over the field of complex numbers. Then take the vector 1i. That's orthogonal to itself because when we take the dot product, we get 1 squared plus I squared, but I squared is minus 1, and then you just get 0. However, a non-zero vector in Euclidean n space, Rn, over the field of real numbers cannot be orthogonal to itself. I have two different things on this slide, a theorem and then something not directly related to the theorem on this second column. So I kind of squeezed two slides into one here. For any coordinate vectors x, y, and z with respect to a given basis in an n-dimensional vector space V over a field F and scalars A, B, and F, the following holds true. X dot y equals y dot x, and ax plus by dot z equals a times x dot z plus b times y dot z. The first part follows directly from the definition of inner product and the fact that we have a field here. So x dot y is basically x1, y1 plus x2, y2, and so on. And since the x sub I, y sub I terms are from a field, you can just switch the order and they equal y1 x1 plus y2 times x2 and so on. And you get this commutativity here. Second part isn't much harder, but we need to go through several steps. So I've just written x, y, and z in terms of their coordinates. Then we have the starting point here. Then we expand this out, as shown here, and take the dot product with the z. And then it's z1 times this first one, all the way up to zn times the last term, and you add them all together. Then I just multiplied the different z1, z2, so on, times the things in bracket. You see here and here. Then I took the terms that had the a and the x's in it, grouped those together, and then the terms was the b and the y's here. Then I factored out an a from this one and a b from this one. And then you can see this is just a times x dot z, and this is b times y dot z. So we have our identity. Then the second thought here concerns something called an orthogonal or a standard basis, or I should say an orthogonal unit basis. And a basis for an n-dimensional vector space V over a field F is a linearly independent subset that spans V. For the specific case, where V equals Fn, the space of n tuples over F, the standard basis is the ordered set, shown here, where the tuples denote coordinates with respect to B itself. 1 is the multiplicative identity of F, and 0 is the additive identity of F. Clearly, the vectors in B are linearly independent. They span Fn, where Fn is equipped with a standard inner product, like the dot product we defined earlier, and form an orthogonal set of unit vectors. So unit just means that the length is 1. I haven't defined the norm yet, but if you just accept my definition here that these are each of length 1, then we have an orthogonal set of unit vectors that form a basis for Fn. Okay, so that was the last slide I have in this lesson concerning vector spaces. I have a few more slides on something called an algebra, and I'll talk about that following this slide. An algebra is a vector space where you can also multiply vectors together in a nice way, which I'll describe in the next slide what nice means. An algebra provides a multiplication rule that defines how to get another vector when multiplying two vectors. So just in terms of review, in a field you have a set of objects like 1, 2, 3.14, minus 5, etc. You can add them and you can multiply them. Everything works as you'd expect. Multiplication is distributive over addition. For example, we have this here. and every non-zero number has a multiplicative inverse. So I've had a whole lecture on fields the previous lesson. In a vector space, which we've been talking about in this lesson, you have a set of objects called vectors, like arrows pointing in space. That's for 2 and 3 dimensions normally. You can add vectors together, we know that, and then you can scale them. In other words, multiply them by a scalar. But you can't multiply two vectors together. So there's sort of a shortcoming here, and that's where the concept of an algebra comes in. So let's talk about an algebra on the next slide. In an algebra, you start with a vector space, so you can add and scale vectors, but then you add a multiplication rule that lets you combine any two vectors to get a third vector, which we write here, u star v, and the third vector is w. So what did I mean by nice on the previous slide? Well, there's three properties that need to hold true here. They're basically distributive properties. So this multiplication we're defining for the algebra, if you take a vector u times v plus w, you can distribute it this way, and then you can distribute it on the right. We have w times u plus v, and you get this here. And then for scalar multiplication, if you have a scalar times u times v, you can distribute the k into or group it with the u, and then take the product with v, or you can distribute the k with the v and take the product with u. And all three of these things are the same. Okay, so that's an algebra put fairly simply. And the main impetus here is that you want to be able to multiply your vectors together. I have a few examples here. The complex numbers are an example of an algebra. Any complex number, they're a vector space, so any complex number, a plus bi, where I is the square root of minus 1, can be thought of as a vector in a 2D plane, two-dimensional plane. You can add them, just add them component-wise here, a plus c, b plus d times I, and you can scale them. You can just multiply any number times your complex number, and any real number times your complex number, I should say, and you get another complex number. They have a multiplication rule. This is standard from complex analysis. You just multiply the a times the c, the bi times the di. Since I is the square root of minus 1, you get minus bd. And then the other terms are bci and adi. So you get another complex number. So that's the multiplication rule. As I said, I won't go through the details here, but multiplication is distributive and works nicely with scalar multiplication. So the complex numbers are a two-dimensional algebra over the real numbers. Some other examples of matrices. The set of all n by n matrices form an algebra. You can add them, scale them, and multiply them. The result of multiplying two matrices is another matrix of the same size. So I'm assuming you know matrix multiplication. It's a little bit strange where you take if you multiply a times b, you take the row of a times the column of b to get an entry in the product. So you have that here, and then polynomials, a set of all polynomials with real coefficients is an algebra. You can add, scale, and you can multiply polynomials. That's just from high school algebra, multiplying polynomials. So, and the different distributive laws hold there. So we have several examples here of algebras. And just the summary here, the different structures and what you can do. I have in a table. Groups you can add or combine elements. And a ring or a field you can add, subtract. This is the additive part here, where you're just adding inverses with such subtraction. and multiply elements. A field is a ring that also lets you divide. That's because you have multiplicative inverses in a field, and you don't necessarily have them in a ring. In a vector space, you can add vectors and scale them by numbers, which we call scalars. And then in an algebra, you can add vectors, scale them by numbers, your scalars, and multiply vectors together in a consistent way. So it's sort of incrementally adding more properties as you go from groups to rings and fields and vector spaces and then algebras. Okay, so that's it for this lesson, and this is the last lesson in my playlist on abstract algebra. It's pretty compressed. This is maybe, I don't know, 25% of what you might get in a one semester abstract algebra class. But again, if you're planning to take such a class, this would be a good introduction. If you're currently taking a class and you're having trouble putting all the pieces together, this may also be helpful. And the reason I did this is I'm working on a book that deals with automatic differentiation and non-standard analysis and category theory. And some of the concepts from abstract algebra come up in this book that I'm writing. And so I wanted to have sort of a compressed overview of some of the terms I'm using. And that's why I did that. Now, the book isn't finished at the time I'm recording this. So otherwise, I would have given you a link to the electronic version. But I will eventually do that, provide a link.